Hello, hi everyone. Can you hear me? Um, Someone? Okay. Hi, Patrick. Thanks for confirming this. And Skyheart. Okay. So thanks all for joining. This is actually number 6 in the series of Stark at Home. And today, the main thing we're going to be covering is Fry, the fast Reed-Solomon IOP of proximity. We'll explain all of these terms. And so Fry is a very particular protocol that solves a very specific mathematical problem, but it's also something that is extremely efficient, and its efficiency is then sort of translated onto efficiency in proof systems that use it. Things like various kinds of Starks, including the Starks that we're building at Starkware, things like succinct Aurora, also the Aurora construction, Fractile, and in sharing these ideas, our hope is that not only those who are interested in applying our very specific version of Starks or understanding it, but even those building very different proof systems might pick up some ideas here that could help in other places, because the objects we'll be dealing with and the sort of transformations we'll be making to them are extremely basic, fundamental, and can be used in other places. So I wouldn't be surprised if ideas that appear in this context can be used in other places, be it in some other system like Plonk or Slonk or Halo or Snarks or something else, to sort of get benefits from a whole bunch of things together. So and another thing that I'm very excited to share with you this time is that we have some recent exciting developments on the analysis of Fry. This is joint work that we just submitted to a theory conference. It's I'll say a little bit more about it. So I'll jump to this screen and start talking. So today is going to be about Fry. Oops. So today we're going to talk about Fry, which stands for Fast Reed-Solomon, and this last thing is IOP. Oh boy, I see I have a big problem with my, just one second, I see that I have a big problem with the speed. So what I'll try to do is just for 1 second try to close a whole bunch of other windows that I have, just in case it might speed things up in some other applications. I apologize. Just 1 second. And then maybe this will speed things up a little bit. So I'll just close a few things. Sorry about that. I hope you bear with me for a minute. Just going to be closing some windows. I should have done this before, but yeah, maybe this will be fine. Sorry about that. Okay, so let me try and go back again, share my screen, and let's hope that this time things will work a little bit faster. Sorry. Okay. Okay, let's see if that helped. Okay, I think this is a little bit better. Okay, so we'll talk today about the fast RS IOPP. And I'm going to explain what these acronyms stand for. And I'm also, so the plan is I want to tell you a little bit about, proximity testing for Reed-Solomon codes. And I want to tell you a little bit about proximity gaps. And I want to tell you a little bit about, the FRI protocol itself. So this proximity gaps, I also want to tell you about, this is the exciting part. So there's some new results, and these are new results that are joined with Dan Carmon. So Dan Carmon works with us at Starkware. He's actually on this webinar as well. Yuval Ishai from Technion, Swastik Koparty, who's a scientific advisor to Starkware, and Shubhangi Saraf, who's another scientific advisor to Starkware, and they are also professors at Rutgers. So these are some new results, not yet published, but we haven't put them online yet, but I got my co-authors agreement to at least mention something about these new results, and I want to tell you a little bit about what they say and how they can be useful also in other contexts, and then we're going to talk about FRI. Okay, so let me just jump back and ask if there are any questions so far, or can you hear and see what I'm saying? Is everything okay? If someone can just chat. Okay, great. Okay, great, thanks. So let's go back and talking. Another thing I want to mention, also with us on this webinar is also Shiri. She's head of marketing at Starkware, and if we need to share any other information, like links to other stuff and so on, so she might jump in and add some information. And also while I'm there, so if you have questions and things are not clear, and someone wants to answer, I don't know, Dan, if you're there. So jump on there. I'll be mostly looking at the whiteboard. So, just from time to time, going back and checking what's going on. Okay, so let's start and describe a little bit about what do we mean by proximity testing and what are these acronyms. Okay. So the problem that we have okay. The problem that we have is that we have this prover that says, I have this function f, this function that goes from some evaluation domain to some field f. And the prover is saying, this function f is an evaluation of some polynomial of degree that is less than some rho times the size of d. So rho is the rate parameter. You could think of, let's say, rho equaling 1/4. So it means that this function, this function that we're giving you Oracle access to. So you can imagine some table that you could access. So this is the function f, and it has a whole bunch of entries, right? And the prover is claiming, this function happens to be an evaluation. The table that you see here, this table right here, it is an evaluation of some function, of some polynomial that is not of full degree. So it's not some arbitrary function. It is a polynomial whose degree is strictly less than the size of the domain divided by 4. So it's a low degree polynomial. And on the other hand, we have the verifier, and the verifier is sort of, standing there just very baffled, what am I supposed to do with this, right? How do I know whether this is right or wrong? Now, one thing that the verifier could do is start reading, the whole table and checking all the entries, and let's say, taking the first quarter of the entries, interpolating them, getting some some polynomial and checking whether this interpolated polynomial happens to evaluate correctly on all these other entries as f is. But we don't want to do that. That's going to be too expensive. We would like some protocol. The verifier would like some protocol by which she can check whether f is indeed low degree as claimed to be. And the prover really has some incentive to convince the verifier that that's the case. So the prover will say, look, I'll just tell me what to do in order to convince you of this. And one thing that has been done in the past, in the past, the prover would ask, the verifier would typically ask for something called it was called a probabilistically checkable proof of proximity, and usually one would denote it by some pi. So it was some other sequence of some other table of entries, and then the verifier was supposed to toss a bunch of coins, make some queries into the verifier would toss coins and then make some queries, query both pi and f, and decide whether this is good or bad. Yes, no. And this object, this pi, used to be called a probabilistically checkable proof of proximity, or proof of proximity, or PCPP. And the main problem was that the size of pi was pretty large. It was like, if the size of the domain equals n, and we'll use this notation henceforth, the length of pi was something like, n times log of n to the to the 4. And that's a pretty large size. And also in terms of the soundness error, the probability of rejecting and finding out when a prover is cheating you, the soundness wasn't too good. But this is one method that could be done. But we're going to describe some other method which is going to solve the same problem. And the problem is that of checking whether a function is indeed a low-degree polynomial. So let me just pause here and ask, any questions so far? And by the way, I urge you to use the ask a question thing. Is anything, not clear yet about the sort of setup and what we would like to do? I'll just wait like a minute or two, and those who have attended previous talks probably recognize this sort of the formulation of the problems that we're discussing. It's all about low-degree polynomials and sort of a prover making claims about them, and then the verifier trying to check whether these claims are correct or incorrect. Okay. So just to make sure, can you hear me? Can someone type? Can everyone hear me? Okay, what if there is a higher? Okay, great. So there's a great question by Adrian. And I also urge you, if you want, there's the Ask a Question tab just below the screen, but I'll answer it also from the chat. So what if there is a higher degree polynomial? Okay, good. Good. Thanks. Yeah. So indeed, so first of all, notice that any sequence of values, for any table that has its entries inside the field f and is indexed by a set d, there exists some polynomial that is the interpolant of that data, right? That's always the case. And generally speaking, all we know about the degree of this polynomial is that it will be the size of the evaluation domain, which is this capital D, minus 1, right? So for instance, every 2 points, there's a degree 1 polynomial that passes through them. For every 3 points, there's a degree 2 polynomial, a parabola, quadratic that passes through them, and so on and so forth. That's all we know. So there will be, to answer your question, Adrian, there will necessarily be some polynomial that happens to explain all of the data. So that definitely could be the case. But maybe to better answer your question, let's define more formally what is exactly the kind of problem that we're trying to solve in a proximity testing setting, right? Because I haven't really defined it formally yet. So now I'm going to define what is the problem we would like to achieve. So proximity testing. So what is it? We have proximity testing. What we want is a protocol. And when we talk about a protocol, we mean something between prover and talking to verifier. They're sort of passing messages from one to the other. And we're also going to allow the prover to send oracles, meaning to sort of give the analog or the abstraction of a USB stick, something that you can query wherever you want, but you don't need to read it at entirety. And so this is called an oracle, an interactive oracle proof. So we want what's called an interactive oracle proof, or IOP. So what it means is that the prover here and the verifier here, and the prover sends over some function f0, and the verifier answers with some randomness, let's call it x0. And the prover answers with some message f1. The verifier sends some x1, and this goes on and on. And then at some point, the prover sends a whole bunch of queries. Meaning, I want to read some entry from f0 and some entry from f1 and maybe 2 entries from the next function and so on. And then we get our answers, which are the entries of these various objects. And then the verifier says yes or no. So this is just a description of an IOP protocol. This is what it looks like. It's a bunch of messages between the prover and verifier. And what we really need is the following guarantees. So So we want two things. We want completeness, which means if f0, which goes again from, it's the very first message, has degree of f0 strictly less than rho times d, then want the probability that the verifier accepts to equal 1, meaning there will be some way to send successive messages and answer queries by the verifier so that the probability of success will be 1. Meaning, perfect completeness we will always accept. And the soundness is the other side, and it says that if the distance of f0 from the set of low-degree polynomials, that we call it the Reed-Solomon code, evaluate over the field f, evaluated over domain D, and with rate r. So if the distance of these things is, let's say, greater than 0.1, then we would like the probability then for any messages f1 up to the very last message, we would like the probability that the verifier accepts to be smaller than, let's say, 0.9. So, or maybe let's make it, just change it to reject. We would like the verifier to find this and to know that something's bad. So we would like the probability that the verifier rejects to be greater than, let's say, 0.1 as well. That's what we would like. So what do we mean by distance? The distance of f from this Reed-Solomon code, what is it? It is defined to be the minimal fraction of entries of the function f that, that need to be changed to make it belong or be, a God honest, to this Reed-Solomon code, F, D, O. So again, let's see what we want. We would like to find some protocol in which the prover and verifier exchange messages. And we would like it to be the case that if the very first message, that the very first USB stick that the prover has sent to the verifier happens to be a low degree, an evaluation of a low degree polynomial, we would like the verifier to accept with probability 1, assuming that the prover, behaves according to protocol and sends the successive messages to be the correct one. So there should be some correct way to behave for the prover in case the very first function is indeed low degree. And then the verifier will accept everything, all the queries that the verifier makes will make the verifier happy, and he will accept. The more interesting and intricate thing, and this was the topic of the last time the last Stark at Home, is that of soundness. We would like to prove that whenever F0 is far, meaning there's a large fraction of entries that you need to change in order to make it a low degree polynomial. So whatever those entries are and wherever they reside, all we know is that there's at least 10% of them that are bad. We would like it to be such that, no matter what kind of messages the prover tries to send us and try to convince us that the very first statement was indeed a low degree polynomial, we would like the probability of rejection to be roughly proportional to the distance of F0 from the code. Okay, so that's basically what we want to do. And let me just explain this maybe pictorially, just to show you. So we could, just for simplicity, from here on, let V, be the Reed-Solomon code, just so I don't need to write it time and again. So it is, it's basically a vector space, right? Because low degree polynomials are closed under addition and multiplication by scalars. So we have this linear space, and it is, it's some subspace of the larger space, which is F to the D, right? All vectors are all functions from the domain D to the field F. So if we view, this large universe as if this is all of F to the D, right? We have a bunch of points here that correspond to V, right? So those are V are these points, right? And they're a small subset of everything. Now we can also, oops, no, I don't want to clear the page. I actually want to draw a circle. So we could sort of surround each one of these, code words. And the Reed-Solomon code is a code word. So we could sort of surround it by some radius. Sorry for not making this very precise, but assume that the center of each one of these circles is assume that each one of these circles is sort of just perfectly aligned at let it be, let each one of these dots be the center of this circle. So what do we have here? Inside these circles, we have all the vectors, all the elements in F to the D, all functions that are relatively close, right? So let's make this radius be, 0.1. So this is radius 0.1, right? So all of these elements are close to the code words. We would like a protocol to be such that, so we're looking for a protocol that is happy, that's cool with all F inside the balls, but not cool and sort of reject all F that are outside the balls, right? That's what we would like. And so we're looking for some protocol that will sort of allow us with forgiveness to accept things that are close to the Reed-Solomon code, but kick out or reject all things that are very far from the read-Solomon code. So that's what we would like to do in this process. Okay, so let me go back and ask if there are questions about what we want to achieve. Any questions? In the meantime, if people are thinking of questions, let me just go back to Adrian's question. What if there is a higher degree polynomial? So now, well, if the function f actually corresponds to a polynomial of degree just one above, I'll leave it as an exercise to see that the protocol should reject it with very high probability. And the reason is, if you take a function that corresponds to a polynomial of degree, your target degree plus 1, you can prove that this is a function that will be very far in Hamming distance from V. Okay, so if you have a slightly higher degree polynomial, that's your input, our protocol should in particular reject it with pretty high probability because it will be outside of all of those balls. It will be somewhere else. It will be very far. What gets more intricate is maybe the prover supplied a function that is a very high degree polynomial, not like target degree plus 1, but maybe as large as all of the evaluation domain. And then what matters is not so much what is the degree of the function f, but whether there is some low degree polynomial that is close in this sort of fractional distance. It's called the relative Hamming distance. Whether there is a polynomial that's close in relative Hamming distance to being a low degree polynomial. That's all we care about. Okay, so I see there are no questions for now, so I'll go back and explain now basically what is this notion of proximity gaps, and then I want to explain how phi works. Okay. By the way, can you hear me? Just again asking because I have like no feedback. So can everyone hear me? Okay, good. So I am jumping back to this question, and okay, now I'm going to describe this sort of cool new set of results that we have with Dan Carmon, Yuval Ishai, Swastiko Party, and Shupangi Saraf. So I want to talk a little bit about proximity gaps. And I'm not going to describe it in full generality. So we have our V, right? V is some property, right? So it's a right? It's a subset of the whole universe. It's a subset of f to the d. And now we could ask, let's look at let's say lines in f to the d. So what's a line in f to the d? Lines in f to the d, they're of the form, maybe u0 plus x times u1. So basically we pick a point, that's u0. It belongs to f to the d, it's a vector. And then we sort of pick a direction. This direction is u1. It's another point in f to the d. And we look at all of these lines. So this is this is u0 plus 2 u1, and this is u0 plus 4 u1, and so on and so forth. We have a sequence of lines. So we say that V has an epsilon delta gap with respect to lines if every line, meaning any u0, u1 that you choose, one and only one holds. So one thing must hold, of the following two. Either the, all points on the line, all things of the form u0 plus x u1 are inside delta balls around V. Okay? Or, so that's one, either one, or two, at most, epsilon fraction of points are in the balls. Let me just go back to the picture and explain what I mean. So we have here the Reed-Solomon, we have here our property V, and we sort of surrounded, we surrounded each one of these elements by a ball, which is sort of the area in which good things could happen. So we say that we have a proximity gap if we look at any line, right? If we take any parameterized line, so for any u0 and u1, if you look at the line that sort of, if you take a line, it's going to be hard for me to draw because this isn't really, what really goes on. So there can only be two cases. Either all things on the line, either all points on the line fall close to, fall within the blue balls. That's one situation. Or else, the complete opposite case happens. Maybe something like this, which means that there can be at most one, a very small number of points that would lie inside balls, but everything else lies outside. So there are two extremal cases, and there's nothing in between. You can't have a line where roughly half of your points look close to low-degree polynomials and the other half looks far from low-degree polynomials. Either all points are close to low-degree polynomials, each and every point lies inside one of these balls, or else nearly all of your points on the line will lie outside the ball. So this is what we call when we have a proximity gap, okay? And what we discuss and prove in this new paper that I hope will be online very soon, and I'll tweet about it and also send an email to everyone who attended this so you can read it and see it for yourself, is we prove that basically Reed-Solomon code, so this this space V does have a very strong epsilon delta gap with respect not just to lines but to other objects, But for the purposes of this talk, lines will suffice. So basically, our theorem. Let me just maybe state it. Though usually I try to refrain from stating theorems. And again, this is a theorem with so it's myself, Dan Carmon, Yuval Ishai, Swastik Koparty, and Shubangi Saraf. It says something like this: the V has, well, let me state it differently. For any radius delta that is less than something called the Johnson bound, I'll just state it, 1 minus square root of rho. This is called the Johnson bound, and those who know error correcting codes will recognize what it means. But I just want to say that when the rate rho goes to 0, this thing goes to 1. So you can have your radius grow larger and larger and larger. You can sort of surround, get these balls that we had in the picture to grow larger and larger. And that makes the result better as sort of this radius grows larger. For any radius delta, V has an epsilon delta gap with the error being very, very small. So the error roughly looks like, I don't want to go, but roughly looks like, let's make it just like 1 over the square root, the size of the field. And this is inaccurate, but I actually do not want to go into exact details, but this gives the gist of it. So the error is going to be extremely small, all the way up to a very large radius. Again, I want to show you this picture. Oh, and I'm going to just prove. I don't know what's going on here. Can you guys hear me? Because for some reason the board stopped working, and I'm now trying to refresh it. Okay, so you can hear me. Join shared board. Yeah, I want to join the shared board. It was my board. For some reason, it's okay. Let me explain. Meanwhile, what a different way to view that theorem. It says, suppose you have even one function that is far from being a low-degree polynomial, and somehow it was committed to, and now it doesn't matter what the commitment is. Then for any other, and that's our u0, okay? And all we need to assume is that this u0 is far from being a low-degree polynomial. Then no matter what other function you're given, that's u1, that's sort of the direction, if you take a random linear combination of the two things, it will be just as far as u0 was. And here's a different way to say the same result. If you have a line, and by the way, you can generalize it to spaces, and you can generalize it to low-degree curves as well. It doesn't have to be a line. It could be some low-degree polynomial that is interpolated between u0 and u1. If somewhere in the space that sort of you committed to a basis for, there is some point that is delta far from being low-degree polynomial, meaning a lot of entries, a delta fraction of entries of it need to be changed in order for it to be a low-degree polynomial, then 99.99% of the space, the points there will be very far from being low-degree. So even one thing being low-degree or very far from low-degree immediately implies that everything spanned by it and any other function, be that other function low degree or far from low degree, will with very high probability lead to something that's completely low degree. So I don't know what happened here. It's sort of, let me just stop sharing for a second, and let me try, maybe that will work again. I'm just going to try and, so it wants me to join that thing. Okay, yeah, now it seems to have worked, so I'm going to go back and share it again. Sorry about that minor glitch. Okay, oops. It's very frustrating that, exactly at the didactic moment that was of most importance, this thing froze on us. But let me enlarge the screen a little bit and repeat what I wanted to say. Here's a different way to say the same thing. And let me just say it here on the side. Okay, it's a different way to phrase the same statement. If let's continue calling it u. If u0 that happens to belong to f to the d is delta far from being a low-degree polynomial, then for any other u1, nearly all linear combinations of the form u0 plus x u1, right? Where, x belongs to f, will be as far, delta far, with no reduction in distance from v. And this is a very strong statement. So if one function is delta far, then no matter what this other function is, nearly all linear combinations that you take, if you try to take this random linear combination, will be just as far. And this is a statement that we prove with pretty strong parameters for very large values of delta and very small values of epsilon. So if you're designing some other protocol, a Planck or a Halo or something like that, or a bulletproof or a snark, you're probably working with low-degree polynomials and doing all kinds of stuff with them. And this kind of statement might be useful for you, right, in your purposes. Even if you're not doing it right now, this could boost things up, speed them up a little bit, make them more efficient. So I hope that's one takeaway. And again, the paper I hope will be online very, very soon, and will, the title will have the word proximity gaps in it. Okay, so we have this generic statement about distance preservation, and we have this target that we would like to achieve of getting a protocol for distinguishing between polynomials that are low degree and functions that are very far from low degree. And the two things seem a little bit similar, right? We know that if something is far from low degree, then taking its linear combination with any other thing, be that low degree or far from low degree, you will still get something that is far from low degree. And we would like to take this component and sort of combine it and get an efficient protocol for verifying if if a function is low degree and kicking out things that are very far from low degree. And that's going to be the next part, and that's where we're going to describe how Fry does it. But I'll stop here again and ask if there are any questions so far about the proximity gaps version and so on. And I see there's already one question, so let me check it out. Does the proximity gap also hold for other correcting codes than Reed-Solomon? That's a great question. So the short answer is that yes, we know of similar results that hold for generic codes. Actually, that's one of the statements that can be, that's one way to interpret results from a previous paper that Swasti, Koparty, Shubangi, Saraf, and myself had. It's called something about worst case to average case reductions to a code. So there's a statement there that gives that. The parameters that we get are much weaker. It doesn't look like the cube root of the field. It looks like something like the third root of the field, and even worse. There is a variant that comes from the Deep Fry paper that also applies to generic linear codes, but it's a little more intricate and it requires something additional. So, but that's figuring out what proximity gaps. So to answer your question, JN, yes, there is some proximity gap, some delta epsilon version that you get for any error correcting code. The parameters for general codes are not as good as we know for Reed-Solomon, but this is a great research area to prove, better proximity gaps for generic error correcting codes. Right, and I think Dara here shared that paper. Great, thanks. Okay, next question. Does the gap still hold if we create a linear combination of more than 2 points? So another great question. The answer is yes, and it gets even better. So there are two things. If you take any k-dimensional space, right, not just a one-dimensional affine space, but like any k-dimensional space, the result holds with the same parameters. Okay, you lose nothing. You can do there's a more intricate sort of de-randomized version of it, which is, suppose you have k points. So there's u0, u1 up to uk. Now, instead of using randomness, sort of combining all of them together, suppose you de-randomize it, and what you do is you take U0, you sample a random x, you look at U0 plus x times U1 plus x squared times U2 plus x cubed times U3, and so on and so forth. So you're taking like this parameterized curve through the points, and you're paying much less randomness. So in that case, you pretty much get the same proximity behavior, but it's not a delta epsilon proximity gap. It's a delta k times epsilon. So your error becomes, k times larger, but k for a small degree polynomial will be something pretty negligible. So it still works. So that's a great question, Rani. Yeah. So you can take more. You can take an arbitrary linear combination, same error. You can even take a randomized, de-randomized curve, and you'll pay only slightly in the error. Okay, great questions. So now I want to sort of, bring these two things together, and like describe how do we get Phi. And of course, when we originally discussed Phi, this wasn't how we described it or so on, but that's a nice thing. And as you look back on stuff, you have a different understanding. And I'm sure that in 5 years' time, we'll probably look at all of this even differently once again, which is great. Okay, so let's go back to Phi, right? We have this. Okay, so actually, we want to use a sort of a rectangle now. Okay, good. So here's our F0, and we would like, we would like to know, is it close to V? We don't know. Well, here's one first approximation, and I want to show you how you can use proximity gaps to sort of argue about it. Well, suppose it is. So, right, suppose F0 really is a low-degree polynomial. So suppose F0 equals some polynomial P of x. And this P of x, right, at the point x. This P of x is of degree rho times the size of the evaluation domain. And again, let's think of rho being a quarter, just to make it concrete. So it's 1/4 the size of the evaluation domain. Good. And let's call this thing, let's make it, let's call it little d. That's our degree. And we're degree less than that. Okay, so let's start seeing what we can do. Well, we can sort of think of it as being the sum of two polynomials. Well, maybe let's call it the low coefficients, x. And what I'll put here is all the coefficients that go, I'm going to split px into the lower half of the coefficients and the higher half of the coefficients. So this is going to be of degree d over 2. Well, less than degree. This degree is going to be less than d over 2. And then I'm going to write here x to the degree d over 2 times p high of x. And this is also going to be of degree d over 2. Cool. So suppose we did that. We're now thinking about the verifier. The verifier would like to know whether this F0 is low degree. So the verifier thinks to herself, well, if it is of degree d, there is a way to write it as the combination of these two polynomials, that each one of them is even of half the degree, right? So now the verifier tells the prover, please, Mr. Prover, please give me an evaluation of, give me 2 more USB sticks. We're in the IOP model. So just give me the evaluation of, this is the low, oops, sorry. So this is going to be low, and this is going to be high. Just give me those tables. Send them to me. Now, what's nice is that the verifier can later on sample some random x and basically check whether, right, you can check whether f0 at this random point x, does it actually equal, let's call this function, I don't know, g0 and h0, right? I just want to put them, I want to be consistent with my notations. So let's call this thing g0, let's call this thing h0. Good. So we can check later on whether f0 at the point x does indeed equal g0 at the point x. Plus, we can compute on our own x to the d over 2 times h0 at the point x, right? This is a consistency test that we can sort of do for any random x of our choice. Cool. So we'll do that later on. But now here comes the punchline. Remember the proximity gap. Well, if we want to apply now the proximity gap result to this. So here's how we're thinking. Well, okay. The distance of f0 from being low degree. So if f0 has, if this is the fraction of points where f0 is far from low degree, it must be the case that this very same region will have some problem either in G0 or in H0. There will be something problematic here, right? Something will be wrong here and maybe a little bit here. And it turns out, so what we can now do is we can apply the proximity gap, and we can think of one of these functions as our u0, as the origin of a line, and ask for a random linear combination of G0 and H0. So let us define F1, which will be this other oracle, to be a random linear combination of G0 plus some alpha 0 of H0 for random alpha that the verifier is going to sample. And now the proximity gap result actually implies, and I'm winging it a little bit here, implies that if f0 is delta far, then with probability 1 minus epsilon, this f1 also delta far, exactly the same distance. And here you're going to have to believe me, I'm going on a limb here. You could think that maybe the distance goes down by a factor of half, but actually it doesn't. It stays the same distance. And this follows from the exact details of the proximity gap, and there's some other correlated agreement property that I don't want to go into. But the proximity gap result gives you this thing. So basically it says that if we started with a problem in which the prover was trying to cheat us and using something that was delta far, we have a very high probability, 1 minus epsilon, that after one interactive step, we will be facing a new function, f1, that is just as far. It is the same distance, right? Up to this, there's only a very small probability of error. And we have now a function that is just as far, but we made progress because this function now has half of the degree of the original function. So we went from degree d, we went down to degree d over 2. And we can now apply this again and go down to degree d over 4 and do this log n many times all the way till we're done, because we have a constant function. And this process is almost what goes on in Fry. The only thing that is missing here in order to get Fry is to see that this wasn't efficient enough, because we went from basically one object of size n in degree d to another object of size n and degree d over 2. And then we'll go to another object that has size n and degree d over 4. So the total will give us, total length of all these oracles will be n log n, right? Because we have log n layers, and each one of these objects is of size n, right? So again, the process, this sort of, the almost Fry protocol will say, well, the verifier knows that if f0 is a God-honest low-degree polynomial, there is a way to write it in this form as a combination of low, the low coefficients and the high coefficients. Please give us the evaluation of the low and the high. Okay. By the way, if we're given G0 and H0, we don't even need f0 because we can sort of reconstruct f0 locally from two entries. So basically, all we need is like two functions. Now we could sample a random alpha 0 and ask to repeat the process with f1. So we can ask for a g1 and an h1 that should represent the low and the high parts of the function f1. The degree has gone down by factor 2, and we repeat this log n times. And this is the almost Fry protocol. It's pretty efficient. It will have a length of n log n. So it's almost Fry. So now I'm going to go back and ask questions, and then I'll just tell you what is this one added trick that gives you actually Fry and an even more efficient version. But let me go back, and I see there is one question, so please go on and ask more questions. Can you describe how this is different from the inner product argument in bulletproofs or Halo? It seems similar in structure, but they don't use the proximity gap result. So let's see. I'm less familiar with Halo. I know how bulletproof roughly works. So in bulletproofs, there is a commitment scheme that is used for sort of a Peterson-style commitment scheme, by which you sort of commit to a polynomial. And then there is a recursive process for evaluating this polynomial, for proving, basically there's a query to the polynomial. You first commit to a polynomial. So you're committing, the prover is applying, is running some process that takes degree many steps and creates a commitment to a polynomial of degree d. Now the problem at hand is to query that polynomial at a random point and sort of make sure that the evaluation is correct. And for this task, there is a recursive process that looks very similar to what I described, of breaking a polynomial into two parts, low and high, or you could actually break it up in any version you want into two sets of coefficients, and then you take a random linear a random linear combination of them and continue the proof. So I would say that there is a similarity. The difference is that the thing you're trying to do in bulletproofs is to sort of polynomial commitment scheme. Here it is not a polynomial commitment scheme, although you could sort of create from a proximity test something that looks like a polynomial commitment scheme. That's one difference. The other difference, which maybe doesn't matter so much for this thing, is that sort of the whole point, I think, in bulletproofs is to sort of use cryptography, special kind of cryptographic assumptions in order to create this problem of solve this problem of polynomial commitment scheme. Here we are in a very different model of interactive oracle proofs, and what we're trying to solve is a different problem. And actually, in the world we're discussing here, we're not even assuming any cryptography. We're just working in this model that is maybe unrealistic practically. But so we have no cryptography at our disposal as we're doing this. That's another difference. But I also want to say that the Fry has one extra trick that I want to describe now that gives you sort of linear size proofs, which is slightly different, I think. And I think that, so I don't remember if bulletproofs uses sort of an FFT style domain and so on, but okay. Next question. The proximity gap implies F1 is delta far, but we want to prove that F1 is half the degree. So is it not the same V as F0? Great question, Guilam. So in the almost Fry protocol I described, the way it would work is that with F1, you will actually measure proximity to a new V. Maybe we should call it V1. And V1 has the same evaluation domain, but it has half the degree or half the rate. So if we started with rate 1/4, F1 should be close. We're asking whether F1 is close to the Reed-Solomon code with rate 1/8. And V2 would be the same question, but with rate 1/16, and so on and so forth. Okay? Okay. Next question. Dara. So can we split into more than 2 parts at each step and use the proximity gap results with a k greater than 2 linear combination? So great question. And the answer is yes, definitely we can. And actually, the way it works is that for this thing, what you need is the curve version of the proximity gap, because the relation, when you take k greater than 2, when you move, instead of 2 to 1, if you move k to 1, what you, sort of the relation between the various f's will not be a linear relation. It will be a polynomial low degree relation, meaning, like, let's see if we can see this. I mean, you will have like x to the d over 4, and then you need to do x to the d over 2 and x to the 3/4 d. So if you think of x to the power d over 4 as sort of the thing that you're using to combine the 4 polynomials, you're looking at a degree 3 curve through the 4 functions that you have. You're going to have some, g, h, whatever, r, and s. And you need a degree 4 polynomial to interpolate through them. But luckily, the proximity gap result holds also in that case as well. Yes, so the answer is you can split it into more than 2 parts, and then you get this sort of trade-off. Your query complexity for, you're going to query, let's say, 4 functions or 8 functions, but your gap goes down by a factor 4 or 8. The degree shrinks faster. So it's a trade-off that you can play with. Great question. And I just want to mention, for instance, that, in the implementations of that we're using in Stark, for instance, in Stark X and other things in the Ethereum Foundation code release, we won't be using the 2 to 1 reductions for efficiency. We sometimes use a k to 1 reduction. Okay. And I see Don is answering a question here. Hey, Don, do you want, maybe let's see if let's try, and I will try to invite Don. This is, the first time I'm trying this, but let me just find Don. And I want to invite Don to, if that's fine with you, Don, to sort of, I'm going to invite Don, my co-author, and also one of our employees at Starkware. Let's see if he's... So Don, if you want to join... how do I... So I'm inviting Don, come on screen. And I'm waiting for him to accept the invite. Don, okay. Okay, so Don maybe will join us soon, and then he can answer that question. But so meanwhile, I will go on and explain the very last sort of, okay, I'm going back to that screen and checking. Okay, so I see Don doesn't want to go on screen, but he answered something on the chat. We'll do it some other time. I would like to explain now what Fry does a little bit differently than what we described here, okay? So we're going back to the screen, and this will be the very last part of the talk. So instead of splitting, okay, let me just move here. So instead of writing, so we could write, F0, we thought of writing it as, as sum at x. We thought of writing it as P low of x plus x to the d over 2 times P high of x, right? So let's just, scratch that. Let's do it differently. Let's write it as P even x squared plus x times p odd x squared. And this might look familiar from the FFT. Now, why is this a little bit better? Because suppose D is closed under negation, meaning that X belongs to an evaluation domain if and only if minus X also belongs to D. So why is this good? Because you see, P0 of X squared actually equals P0 of not X, of minus X squared, right? And the same thing with P1. So basically what it means is that, if this was F0, right? If this was F0, we could now have two functions of half the degree that we can call them G0 and H0. And now they are half the size, and G0 is supposed to be the evaluation of P0 x squared, and H0 is supposed to be the evaluation of P1, right? So this is supposed to be P0, this is supposed to be P1, and each one of them is sort of to be evaluated on all of D. But the point is that because P0 only cares about the squares, because P0 is a polynomial in squares, it means that you only need half of the domain because, you only need to pick whether you want X or minus X, it will be the same value. And you can still get, so from, we can get F0 of X will equal G0 of X plus X times H0 of X. That's cool. But we can also get F0 of minus X from those very same two entries. It is G0 of X minus X times H0 of X. Yeah. Well, assuming this is an X squared, whatever, right? The entries here are squares, maybe. Maybe this is more correct. So the main point here is that the way we saved is previously we had sort of, right, in this world, we had two objects that were of size, n, but half the degree. And now here we have, so the rate has gone down, but not the block length. And here in Fry, so this is the way it's really done in Fry, right? Here we have two objects that each one of them is half the size, but the same rate. So half size, same rate. And what we do is we can still have this consistency test. We can, for a point X here, and actually for minus X, we can sort of go here to X squared and go here to X squared. And from this, we can sort of reconstruct both values and check consistency. So that's one way we can get consistency in Fry. And then we can apply, again, the proximity gap version and ask about F1 that is supposed to be a random linear combination of H1 plus alpha times G1. And this is the size of F1 is actually n over 2. So in Fry, what we have is we have total size equals n plus n over 2 plus n over 4 plus, so on and so forth. And this actually is equal, less than or equal to 2n, right? It's a geometric sum. And that's how you get smaller size. So we went down from size n log n to size O of n using pretty much a similar thing. And the soundness is what the proximity gap version gives you. So that gives you basically the way Fry works. And that was the last topic that I wanted to cover here. So any questions? So I see here Robert is asking in the chat, what is rate in half size, same rate? Okay, the rate of an error correcting code is defined to be the amount of information divided by the block length. In the world of Reed-Solomon codes, the amount of information is degree plus 1, because basically, for a degree D polynomial, you have D plus 1 coefficients that you can play with. And then the evaluation domain is, for us, it was the size of the capital D, the size of the evaluation domain. So what we did when we said we go to half the block length and same rate, we said F0 had rate, let's say 1/4, which means that it was of some degree little d, and the evaluation domain was 4 times larger than little d. After one step, we went to this new function F1 that has the same, its evaluation domain is half the size of capital D. Now its evaluation, the evaluation domain's size is actually n over 2, because it's comprised of all squares, but we made sure that D was closed under negation. So x and minus x are sort of mapped to the same element, and we have something of size half the size. But the degree has also gone down by a factor 2, which means that we stay with the same rate. We shrunk the evaluation domain by a factor 2, and we shrunk the degree of the target Reed-Solomon code that we're looking at also by factor 2. So we stayed with the same problem, meaning the same rate, over an evaluation domain that becomes half the size. Okay, so I see the question also appear there. Okay, what other applications might benefit from Fry? So Fry is a transparent, post-quantum secure, super efficient protocol for checking proximity to low-degree polynomials. The use cases that I'm aware of right now are things, and it's in this IOP model, so there's already some implicit prover and verifier playing. So I would say that you can apply it to a whole bunch of ZKPs out there. So not just, you could also apply to maybe non-transparent ones, or to other kinds of things that are not necessarily post-quantum secure. You could try to sort of break polynomials up. They show up in a whole bunch of places. So you could apply these techniques elsewhere. That's one place that they could show up. There are other areas that are also a little bit similar. There's this thing called verifiable secret sharing, and all kinds of anything with a V, verifiable random functions, verifiable delay functions, verifiable. If you have a V there that stands for verifiable, or if you have a P there that stands for proving, it could be useful. Another area I think where it could be useful is somewhere in secure multi-party computations, which are sort of a generalization of zero-knowledge proofs. Basically, in a zero-knowledge proof system, there's just a prover making a statement and proving it to the rest of the world. In a secure multi-party computation, you have a bunch of players, and each one of them has part of the inputs, and they sort of need to compute together. So they can definitely, I can see, I don't have a concrete application in mind, but a lot of the techniques there also use low-degree polynomials here and there. So I could see Fry, playing a role there somewhere. Those are two obvious areas: secure multi-party computation, general ZKPs, as well verifiable secret sharing. Okay, more questions? So. As I said last time, I think we're going down to once every 2 weeks for this thing. It's there are other things that all of us have to do, and it takes me a lot of time to sort of mentally prepare for this. So next time, which will be in 2 weeks, I would like to offer to go over, the sort of our view, or my view of the Cambrian explosion of ZKPs, sort of the different kinds of proof systems out there, and their sort of pros and cons, and the underlying cryptography. It's something that I wrote a blog post about, and I've been asked about it quite a few times. So that's, I think, a topic that I'd be very happy to discuss, again, informally. If there are other things that you would like for the time after that, definitely would be happy to hear about those. You can shoot me an email or use this chat room. I'll stay around for a little while. Yeah, so I'm enjoying this, and I hope you're as well. And thanks so much for spending time listening to this and asking great questions. And I hope to continue collaborating with all of you guys also, by email and other ways and so on. So thanks, everyone. Okay, and I will end the broadcast.